And we'll go from current slide. And we'll try to get the projector to work. Okay. Oh, this is a long way down. Okay. Don't tell me it's going to do this mess again. Let me try one more time and see if it'll connect. Not doing anything. So let's try this again. I don't know what the story is here. Okay, did that do something? Yes. All right, and we still got power. It's amazing how many iterations you have to go through. All right, first a couple of announcements, and I think these are going to be pretty much it for the term, I'm hoping anyway. Have you done student course evaluation? All right, good, excellent. Okay, number 2. My office hours have been wacko recently because I've had to be coming to the Birmingham campus just about every Monday and Tuesday and Thursday afternoon. So they haven't been like we're posted on my syllabus or on the locator card. But I think those are basically over with now. So here's what they're going to be for the rest of the term, which is not very long. Let's start with tomorrow and Monday. That's Wednesday and Monday. As normal, as always, nothing changed. Well, no, a little bit changed, but not much. Nothing changed. 8 to 8:30 in the morning and 5:30 to 6 in the evening. Monday, or tomorrow, Wednesday, and next Monday, those are it. All right, Tuesday and Thursday, those are ones that have been walked all over, but I got the last thing done today that is been messing with my schedule. So from now on, like in next Thursday and next Tuesday, okay, they will be 10:45 until 4:15. I was saying 4:30, but I found 4:30 just made me too late getting over here, so I've changed it to 4:15. I'll be on the Birmingham Bessemer campus 10:45 until 4:15. Then I'll drive over here, and I should be here before 5 o'clock, hopefully set up, ready to go. Hopefully. Okay. So we're back to normal there. Now, we have class today, and we have class on Thursday, and we have class next Tuesday. Okay? Hopefully we'll finish basic electricity in those 3 times. Maybe get a little bit going into the next chapter, 16, which is, I think, circuits maybe. 17. It's chapter 18. Look, let me find out what the electricity. 18. No, 18 is magnetism. Okay, so we may get a little bit into magnetism, but basically, I think chapter 17 probably will be your last test. Okay, so I hope to give this to you, maybe even Thursday, just to give you a weekend that you can work on it, at least the first part of it. And then once we have class the next Tuesday, then you'll be able to finish all of it, I think. So that's what that will be, class. All right. Now, technically, your final exam is due, which will be chapter 17 test, the following Thursday, 1 week from day after tomorrow, okay? Now, I will be here as normal. Now, let me also tell you this one. Wednesday is technically the first day of finals in my book. Okay, I have 3 classes on Mondays and Wednesdays, and yet they've scheduled an academic standards meeting, something like 1 o'clock Wednesday afternoon. So that means I won't be on the Bessemer campus to be collecting finals. I will be over here in a meeting. So that means I will be on this campus, not this campus, but West Campus. Basically, I think academic standards meeting, they won't get over with before 2 o'clock, and it may be closer to 3. But anyway, from 3 o'clock until 6 o'clock, I'll be over on the Birmingham West Campus. So if you want to turn in your test that day, I'll be over there. Or if you want to just wait till Thursday when we normally meet, I'll be here. I'll be here by 5 o'clock, and I'll be here until at least 6:30. I'll be grading papers, putting grades in Blackboard, doing whatever, so you can come by anytime and turn in your test. If you want to turn it in early, Wednesday I'll be on the Bessemer campus from 8 until probably around noon. Then I'll come over for that meeting that's at 1, probably 12:30. Then I'll come over to the meeting from 1 to, I'm guessing 1 to 3, and then from 3 to 6 I'll be on the Birmingham West Campus. Do you know where Dr. Pruitt's office is? Okay. It's in the B building, that long building. You know where that one is? Okay. The B building, the end toward the gym and the tennis courts and the baseball field. Up on the upper level, there's only 2, one lower level, one upper level. Up on the upper level, the last door before you go down the stairs to go out the building. So I'll be there basically from 3 to 6, grading papers, that kind of stuff. And then I'll be on Thursday, Bessemer campus from 8 o'clock until 4:15. Then I'll drive over here. I'll be here from 5 till 6:30. So whenever you want to turn them in, that's where I'll be and when I'll be. If you have any question about any other time, ask me and I'll tell you my best guess of where I'll be then. Okay. Any questions? Oh, yeah. You ready? Wow. Good deal. Thank you. Okay. Okay. Let me, before I forget to do it, get have you heard from Brianna since? That and here. Oh, hey.
Brittany called. She in traffic too.
Oh.
So she's on her way.
That's Brianna?
Yes.
Okay. All right. Let me get you marked here.
It's ugly out there.
It's what?
It's ugly out there.
It's what out there?
It's ugly, the traffic.
Oh, really?
They got backups everywhere.
Really?
Yes.
Have they been having rain? It doesn't look like any here.
No, they driving fast and just wrecking. Dr. Fowler.
Yes.
I left my test and my paper in Ozark. I was trying to get up here because I had to work tonight and left it. Do you mind giving me another sheet?
Okay. Of that last test?
Yes, sir. I'm going to have to redo it.
Okay.
But I have that to you Thursday.
Yeah, there's no sweat on that. I don't think Haley got one, so if she comes in tonight, I'll have to make another copy for her. If she doesn't come in tonight, I'll make a copy when I go put up the court.
Yes, sir. Thank you so much.
All right, thank you. Okay. Hate to go over this again, but just so you'll get to hear it too. I'll try to make it a little shorter this time. My schedule for the rest of the term, okay? Let's start with tomorrow morning, and this will be good on Monday morning too. Yes. Wednesday and Monday, Bessemer campus, office hours, 8 to 8:30, 5:30 to 6. Nothing has changed there, okay? I'm in class basically all day, except for from 8:30 to 5:30. In class 9 solid hours almost, with 2 5-minute breaks. Okay, that's it. Okay. Thursday and Tuesday, I don't have to come back to this campus either day. I've been having to come just about every Tuesday and Thursday. So basically my office hours now will be, I'll be in the office from 8 to 8:30 on Tuesday and Thursday also. But then I have a class in the morning from 8:30 to 10:45. Then from 10:45 until 4:25, when I'll leave to come over here, my office hours will be on the Bessemer campus. Then I'll come over here and try to be here before 5 o'clock, get set up, and we'll have class today, Thursday, and Tuesday. Okay. Now, I'm going to try to have your test on Chapter 17 ready for you on Thursday, day after tomorrow. We won't be through with 17, I don't think. So don't sweat the things that we haven't done yet. Just hang on and just work on those you can over the weekend. And then we'll have class on Tuesday, and then I'll get into the rest of that. Well, I guess that would be it. All right, so let's get to Wednesday of next week. That's when final exams actually start. So I'll be on the Bessemer campus from 8 in the morning until around noon. No, 12:30. At 12:30, I've got to come over here to the West Campus, because they've called an academic standards meeting. I'm supposed to be collecting exams, but I'll be over here. So once that meeting's over, it'll be, I'm guessing, about 1 to 3. So after 3 o'clock, between 3 and 6, I'll be on the Birmingham West Campus. Do you know where Dr. Pruitt's office is?
Yes, sir.
You do? Okay. My office is next to his, behind the secretary's desk in the copy room. That's where I set up and work over there. So if you do finish your test and you want to turn it in Wednesday rather than waiting till Thursday, I'll be there approximately from 3 to 6. I don't know exactly, but I'm guessing 3 to 6. Then on Thursday, I'll be on the Bessemer campus from 8 o'clock until 4:25, and then I'll be over here from 5 to 6:30, just like normal. So if you just want to turn it in as normal class time, you can. And we won't have any thing else. Now, the only other wrinkle to this that I wonder if you would want to do, and you don't have to, if everyone does want to turn in their test Thursday evening, 5 to 6:30 sometime, and that's all we're going to be doing.
How do we get our grades back? Test. You gonna put them on?
Yeah, I'll put them on Blackboard. In fact, I'm hoping next week to get Blackboard caught up. I'm hoping. Okay. Now, because I'm through with my hearing and all that kind of stuff, okay, I've got to run downstairs, okay, and I just gave your test away, so I've got to go run you off another copy. I'm going to put this on pause, and I'm going to run. But let me go over again. Let me start again. What the schedule looks like for the rest of the term. Did I mark Haley here? Poor Krishana has heard these announcements almost 3 times now, so let me go over, and then as soon as I finish, Brianna will come in, right? We'll do it one more time. Okay. So let me sort of quickly, if I can. One other thing too. The last test, I returned 2 of those last time, and I can give you yours tonight because Brianna turned hers in. Okay. All right. So, let me explain. I lost a penny. How things are going to look for the rest of the term. Tomorrow and Monday, back to regular office hours on Monday, and they haven't really changed. Office hours on the Bessemer campus, 8 to 8:30, 5:30 to 6. The rest of the time I'm in class all day Monday and Wednesday and Monday. Okay. Thursday and Tuesday, I've been having to come over here to the Birmingham campus because I've had to get signatures, I've had to I've had meetings and various things. All that I think is over with, okay? So my office hours go back close to what they were before, okay? I have office hours on Thursday and Tuesday, 8 to 8:30, and then 10:45 until 4:15 on the Bessemer campus. I used to say 4:30. I'm saying 4:15 now to give me a little more time to get here and get set up. And then I'll be here, 5 to 6:30 as normal. Now, that covers tomorrow and Thursday, Monday and Tuesday. Regular class days, those days. So we'll have class Thursday and we'll have class Tuesday. Now what I'm going to try to do is have your test ready for you on Thursday, and then at the end of the class, it will be Chapter 17 tests. At the end of the class, I'll give them to you so you can get started on them over the weekend. You're not expected to finish them just because we won't have finished covering the material, I don't think, but you can get started on them over the weekend. And then when we have class on Tuesday of next week, that will be the last class. Okay. So let's get into finals. On Wednesday, I'll be in my office on the Bessemer campus from 8 o'clock in the morning until about 12:30. Normally I wouldn't be through at 12:30, but they've called a meeting over here on the Birmingham West campus, and here she is. Okay, so I'll start this over again. All right, if I can get up. Someone lowered the chair here so I can hardly get in and out of it. All right, perfect attendance tonight. Way to go, team. Okay. All right. Now, does anyone need a light on? Because I can easily turn one on. I know it's getting a little dark. Are y'all okay? Or you want it on? All right, what I was doing, and this will be the last time because everybody's here to hear it now. Let me go over how the term is going to end. Tomorrow and Monday, office hours is normal. Bessemer campus, 8 to 8:30 in the morning, 5:30 to 6 in the evening. That's tomorrow and Monday. Last 2 days of class for Monday, Wednesday classes. Then Tuesday and Thursday, we go back close to what normal was before because I'm through with all my meetings, except one, and through with all the other things. So my office hours will be on Thursday and Tuesday, 8 to 8:30, 10:45 until 4:15, and then I'll be over here from 5 to 6:30. That's Thursday and Tuesday. Now, the last 2 days of class for the summer, well, the last 2 days, those are the last days of class. The last 2 days of finals will be Wednesday and Thursday of next week. On Wednesday, I'll be on the Bessemer campus from 8 until 12:30. Okay? Unfortunately, they called a meeting for 1 o'clock over here, so I'll be over here on the West campus at a meeting from probably 1 to 3. Okay? They just said the start time, but it's a long meeting, so it'll probably go to 3. After that, I'll be in B122, which is Dr. Pruitt's office. If y'all know where that is, I'll be there from about 3 to 6. Okay? Whenever the meeting gets through, I'm guessing around 3 until 6. So if you wanted to turn in the paper then, your last test then, you can. I'll be over there. I won't be on Bessemer. I'll be on Bessemer 8 to 12:30, but Birmingham West, approximately 3 to 6. But then on Thursday of next week, not this Thursday, but next week, I'll be on the Bessemer campus from 8 in the morning until I leave there at 4:15. I'll drive over here, and I'll be here from 5 to 6:30 as normal, just for you to turn in your test. Okay? Now, just give me a feeling on it now. Are y'all feeling like you'll probably want to turn in the test that Thursday evening, or you want to try to catch me Wednesday? Yes.
Which test are you talking about?
The last test, Chapter 17 test, basic electricity. Okay? I'm going to try to give it to you day after tomorrow on Thursday so you can start it on it, and then we'll have the last class on Tuesday, and you can finish it up and turn it in then. Turn it in.
This Thursday, I won't be here.
Okay.
We're going on vacation.
Uh-huh.
So I'll be able to turn in.
You'll be able what?
If somebody can take a picture of the test
Right.
at 17, I can start on it while I'm on vacation.
Okay. All right. We'll try to do that. Someone will do that. I don't typically bring my phone to classroom.
Sharon says she'll take a picture.
Okay. All righty. Okay. Now, do you think you'll be turning it in that last day, Thursday evening, around 5 to 6:30?
Next week?
Yeah, next week.
Yes, sir.
Everybody think that? Okay. Do you want to try to have pizza that night too?
Yes.
We're not going to have class. We'll just be turning in a test. So it seems like just a waste just to drive out here to turn on a test. You want to eat? Okay. Is pizza okay, or would you rather have something else? I could do Subway. I could do...
Pizza's fine. Can't be choicy.
Say again?
Say pizza's fine. We can't be choicy.
Yeah. Okay. What kind would you like?
I don't do pork.
You don't do pork. So cheese pizza?
Chicken or cheese.
Okay. I usually pick it up at, well...
Oh, man, what do y'all do pork? I do, but I just like the cheese. I just okay. Yeah, I'm just say pepperoni. I can't eat straight cheese. I'm gonna be stuffed up.
Okay. So 1 pepperoni and 1 cheese?
That's fine.
Is that all right?
Yes, sir.
Okay. I usually do Papa John. No, not Papa John's. Little Caesars, because it's close to Bessemer.
That's fine.
Okay. So that'll be all right?
Yes, sir.
So if I'm a few minutes late, it's because they're running sort of late. Okay. But otherwise, I'll be here as soon as I can, and we'll just have pizza, and y'all can turn in the test. And while y'all are eating pizza, I'll try to grade the test so you can see your scores. Okay? You want to do that? Okay. I'll try to be here by 5, but if not, I'll get here as soon as I can. All right. That said, basic electricity, chapter 17. 17.1 starts with electrification, they say, was first studied 2,500 years ago in ancient Greece. And here's what they discovered. Does anyone know what amber is? It's fossilized rosin from, say, a pine tree or something like that. Okay? And they found out if they rubbed an amber rod with a wool cloth, they could shock people with it. Okay? Now, that wasn't very exciting. Well, it may have been sort of exciting if you got shocked, but that's all they knew about electricity, that if you rubbed amber with a wool cloth, then you could shock somebody. And for centuries, that was about all electricity was. It was a parlor game. If you snuck up behind someone and touched them with the rubbed amber rod, they would get shocked and jump, and people would giggle and laugh and scream or whatever. Okay? Now, we used to do, when I worked for Southern Research Institute, we did a lot of research down in Central Florida, and we usually stay at, okay motels, but they were pretty cheap. And they typically had the synthetic carpet that, out in the hallway, and because of storms and stuff, I guess, they built the building out of steel, not wood, but steel. And when you rubbed your feet, especially if you had sort of rubberized soles on, across that synthetic material, and then you reach for the doorknob, it would shock you, okay? And I found a way to get around that. I would pull out my key, any kind of key, car key, house key, any kind of key. I don't have a key on me right now. When I got near the doorknob, I would hold the key near the doorknob, and then it would shock the key and not me. I could see the little spark go. That's also electricity. And I bet you, every one of you has taken clothes out of the dryer and had static clean, right? That's static electricity. Now, what's going on with all those things that either shock you or stick things together? Well, the principle is basically what we call static electricity. Now, this is a rendition of what an atom of lithium looks like. Now, that's not quite accurate, but it's okay. Okay? What these things represent are the nucleus, and in the nucleus for lithium, they don't say it's lithium, but I'm just telling you it is. There are 3 protons. Now, with lithium, there's usually 3 neutrons too, but neutrons don't have any charge, so they've left them off of this picture. So there'd be 3 other balls about like that size in the center. Now, don't take this picture as being dimensionally correct. It's just a representation. If you were really making it dimensionally correct, you would not be able to see these little blue balls at all, because they have almost no volume whatsoever. Okay? The red balls in the center are tiny, but they're much bigger, much bigger than the blue balls around the thing. Well, these are the positive protons, and like I said, there's usually 3 neutral neutrons also in the nucleus. That's in the center. And then there's 3 electrons, and they're negatively charged, and they're flying around on the outside. Okay? Now, just as a reference, almost all the mass of that atom is located in that tiny little nucleus stuck away there in the center. Just about the entire mass. The electrons have almost no mass whatsoever. They have a little, but it's not very much. Okay? But they fly around the nucleus, and they take up just about the entire volume of that atom. Okay? So they have almost no mass, but they take up almost the entire volume. The little teeny nucleus is stuck in the very center, has very small volume, but almost all the mass. Okay? This is what we call a neutral or normal or uncharged atom. I'm just telling you that represents a lithium atom. Not that it matters. Okay? Now, if you were rubbing lithium, which you usually wouldn't do, with some type of material, and you knocked off a negative electron, now you have 3 positive protons in the center and only 2 negative electrons on the outer part. So this would now be an atom with a positive charge, because you have 3 pluses, 2 minuses, that would have a net positive charge. That's what happens in your dryer. That's what happens when you scuff across the floor. That's what happens when you rub amber with wool. You're knocking electrons off of one substance onto the other. Both of them wind up charged. This would be a positive charge because you have more positives than you do negative. And that can happen. And it does happen with lithium. Now, this doesn't happen, but they're using this just as an illustration. If you were to rub it with some material, not that you would lithium, and you picked up an extra electron, now you have 4 negatives and only 3 positives, and now that would be a negative, an atom with a negative charge. These atoms with charges we give a name. This is called a positive ion, I-O-N. This is called a negative ion, I-O-N. This is called a neutral or normal atom. No charge, no net charge at all. Does that make sense? So what happens with rubbing amber with wool? You're knocking electrons off the wool onto the amber, and that's why you shock people. When you're scuffing along the floor in the cheap hotels, your shoes will probably be picking up electrons off of that. You become negatively charged, and that's why you shock yourself when you touch the doorknob. Okay? Now, in the old days, I don't know that I've noticed this lately, but in the old days, when they had those cheap naugahyde seats in cars, and you scoot across with a polyester pants and reach for the door and shock yourself, you were doing the same thing. You were either knocking electrons off, becoming positively charged, or picking up extra electrons, becoming negatively charged. And that's why you got shocked. Okay? So, one guy, and you usually probably don't think of him this way, that was instrumental in understanding this early on, he was a patriot. He was a newspaper man. He was a postmaster. He was all sorts of things, plus an inventor, plus a scientist. Benjamin Franklin first referred to the electric charges as being positive and negative. Ever since then, everybody's always referred to them as positive and negative charges. And if you see this picture in the text here of the guy reaching for the doorknob, and you see a little spark coming off his hand, that's exactly what I was describing at the cheap hotels in Florida. Okay. Now, this is not a fair question, but I'm going to ask it anyway. Has anyone ever seen what they call a cobweb? Oh yeah, I've seen it in our house a lot. Yeah. And guess what? That's not a web at all. Those are tiny little dust particles that stick to each other, one on the other, to the other, to the other, and they're just a chain of dust particles. Why? Because dust particles, being so tiny, they have a net charge, and the positive will stick to a negative, and then a positive will stick to that negative, positive will stick to that negative, and you wind up with what they call a cobweb. You touch them and they fall apart because the charges get distributed. That's also static electricity. All right. They do a thing in the book called picking up dust, but I thought, let's just talk about cobwebs. Now, there are two types of electric charges, and what we're going to talk about now is a device called an electroscope. Now, you don't need to know what an electroscope is. This will describe it for you. We don't have one. I won't show you one, but pay attention to what they say it does, and you may find it hard to believe, but it does exactly like this. Okay? Now, you can make one really simply. This is called an electroscope. Let's say that we have a ball of wood pith that would sort of be something like cork or something like that. Just a ball hanging there. Okay? It's hanging from a string. Just hanging there. Just dangling there. Okay? Now, what if you were to get a rubber rod? This time we're going to use rubber rod. And let's say you rub it with silk or something like that. So that rubber rod, actually probably fur or wool would do just as well. Rub it with that. Or, now if you have not very oily hair, fairly clean hair, and it's a fairly dry day, we don't have this very much here in the southeast, but if you comb your hair with a rubber comb, you can also make it slightly negative. So you take this rubber rod and hold it against that you've rubbed with wool or rubbed your hair or whatever, and touch it, you make that wood pith negative. Okay? Now, if you do that to two electroscopes and then bring those electroscopes near each other, those wood balls that were just hanging down here like this, you bring them close to each other, but you've charged them both, now they move away from each other. Okay? Why? Because of this. Like charges repel. Like charges repel. So if you made both of those wood pith balls negative by that same rubber rod, now they move away from each other. And that's called like negative charges repelling. Now, let's say we get a glass rod and you rub it with silk. The silk is going to take the electrons away from the glass rod, and what's going to happen, you're going to make that wood pith positively charged. Okay? You do that, and they call this process, when you touch a charged object to a non-charged object, transfer the charge, we call that charge transfer by conduction. Okay? In other words, either the excess electrons, as in the B up there, move on to the ball, or the deficit of electrons shares deficit with the glass rod and it becomes positively charged. Okay? So, here you have one wood pith ball that's negative, another one that's positive. Guess what they're going to do? They're not going to repel each other, they're going to attract each other. Not just hang there, they're going to try to get as close as possible to each other. Why? Because unlike charges attract. Like charges repel, unlike charges attract. Okay? If you did two of these wood pith balls with a glass rod and make them both positive, then they act just like the two negatives. They repel each other. They don't care whether they're positive or negative. They just care whether the other is like or dislike or unlike. If they're like each other, they repel. If they're unlike each other, they attract. Whether one's positive or negative, the other's negative or positive, it doesn't matter, they're going to attract. Whether they're both positive or both negative, doesn't matter, they're both going to repel. That device is a central electroscope. Okay? Now, so that's one way you can charge an object, simple electroscope, actually touching it with a charged object. That's called charge transfer by conduction. Okay? Now, here's another way you can do it. This is called charging an electroscope by induction, not conduction. Conduction means you're conducting the charge when you touch it. Okay, so here's what's going on here. Here's an electroscope, and this one has two gold foil leaves. You could use other things other than gold, but gold can be hammered out very, very thin. You have two gold foil leaves, and as long as they're just there, and by the way, let me explain the rest of this. You have a metal ball on top, and by the way, metal is a good conductor. Okay? Gold is a good conductor. It has a metal stem. That's a good conductor. But here we have an insulator, say rubber or something else, that is keeping the charge from moving from these good conductors to this good conductor. Well, here's a metal case, which is a good conductor, and a glass window, which is pretty much an insulator, the two gold foil leaves. Okay? It's called a gold leaf electroscope. So here's what we're going to do. We're going to take a rubber rod that is negatively charged. You rubbed it with wool, okay? And you got it to be negatively charged. And you're just going to bring it close to this metal ball. All you're doing is getting it close. Well, what's going to happen? This negative charge rod is going to attract the positive charges up here, okay? And the positive charges are going to be attracted to this. You don't touch them. You just get them close. It's going to pull them up here, and the minute it does that, that makes these charges down here negative. Okay, now what they didn't explain here, the metal stem goes all the way through this insulator. So the metal stem is in touch with, in contact with, a good conductor with the gold foil leaves. So if you get the rubber rod close to this, the positive charges go up here. In actuality, the negative charges leave here. They rush down and try to get away. Now that the two gold foils have extra negative charges, they have the same charge, so they split. They get as far apart away from each other as they can. That's called induced negative charges repelling. You didn't touch this to anything. You just came close and it induced a charge, positive here, negative here, so they split. Now, if you were to take a glass rod that you've rubbed with silk and made it positively charged, now when you hold it close, don't touch it, hold it close to this electroscope, the metal up here, the negative charges are going to move up like this, trying to get close to those positive charges because they're attracted, leaving positive charges down at the bottom, and it does the same thing. But for a different reason. Now they're both positive, so they split. Before they were both negative because they split. Because you've induced a charge by bringing that charged rod near a good conductor that conducts the charges either away from the negative charge or toward the positive charge, and when they do, that leaves the electroscope negative or positive. Induced charges. You didn't touch anything, you just got them close. You move the rubber rod or the glass rod further away, they go back, because now there's no longer anything inducing a charge. All right, and they do a little blurb on Benjamin Franklin again. You probably heard his experiment where he went outside in a thunderstorm and flew a kite, to see if indeed that lightning, which he thought it was electricity. He was a smart dude, though. He hung a key between him and the thing and let the key be near the ground. Sure enough, when that lightning struck, it went to ground on the key, and it didn't go to the ground through him. Otherwise, he would have been a former smart guy. Okay, it would have killed him. Okay, electrocuted him. Okay, so that's induction. All right. Now, here's what we're going to do now. This seems a little bizarre. We're going to take that rubber rod that we've charged negatively. We hold it near the electroscope, near the good conducting there. Ooh, goodness gracious. Oh, that hurt. The electrons are going to flee away from that because like charges repel. So you leave positive charge here. Your electrocoat splits because these are now negative because the electrons have all gone down there. Okay? That's induction just like we saw before. Now you do something a little bit different. You take your finger. You don't touch the rod to that. You take your finger and touch it. You are a good conductor. Your blood has lots of salts in it, okay? So it conducts really well. You're sweaty. You're a great conductor. So you touch that, and what happens now, and it looks like to me they've got these a little bit backwards here, but we'll let them live with that. Actually, what in my mind happens, the electrons from your finger move over here to balance the positive charge there. They show electrons fleeing. I don't believe it. I think the electrons go this way, and now that neutralizes that, the gold foil goes back together again. Okay? Okay. Now, you bring this close, but this whole thing is now net positive charge. The way they do it, I'm sorry, no, is okay. The electrons has now electron shortage, they say. I think it has excess. Okay, so this thing is neutral again, and these go back together. You pull the rod away, get rid of it. Now, since you lost electrons before the way they're describing it, now this is net positive, and now those foils split again. Okay? Because like charges repel each other. Okay. Now don't get too wrapped up in here. This is just explaining that basic principle. Like charges repel, unlike charges attract. Okay? Conductors conduct. Sometimes electroscopes induct. You don't have to actually touch, you just induce a change. Okay. Now, there was a guy, I think he was pretty amazing. His name sounds very, very Dutch. Van der Graaf. You know where he was from? A physicist born in Tuscaloosa, Alabama. And he invented this device called a Van der Graaf generator. That's it right here. Now, this is a laboratory model. What happens here, you have a band down here that moves at very high rates of speed, and it's brushing against this metal container here, and when it does that, it leaves a charge. A net charge, just like that electroscope did. Okay? So here's what's happening. Your source of electrons is down here. There's a brush that's hitting things. The motor is turning this belt really rapidly, and this thing is negatively charged. All of it negatively charged. And look what happens when these kids put their hands on it. Now, they don't just put it there. They had them there before you turned on the machine. Okay? And as you turn on the machine and it starts getting more and more negative, their hair becomes negative. So it starts flying off in every direction. Okay? Why? Because like charges repel each other. Van der Graaf generator developed by a guy, physicist from Tuscaloosa, Alabama. Okay. And people all over the world know about Van der Graaf generator. I never knew until I taught from this book that he was from Tuscaloosa. All right. Now, this next slide is quite a few pages away. And by the way, that was 17.1 and 17.2. We haven't hit a single problem yet. Yeah, several pages away. So I'm going to leave. Yes.
On 17.3 is a problem right there.
Yeah. We're starting 17.3. Okay. We've done 17.1 and 2 and not a single problem yet. Now we're going to get into 17.3, and that's where the problems begin. The exercises begin. Okay. So let me leave this slide here. We'll come back to it later. Go to our whiteboard slide and go from current slide here. All right. 17.3 is going to be talking about a pretty famous French scientist named Charles Coulomb. Now, I want you, if you would, if you got your books handy, go back to the little blurb they did on Benjamin Franklin and notice the dates of his life, 1706 to 1790. So, boy, 84 years old was pretty old back then. Okay, look at Charles Coulomb, 1736 to 1806. So he only lived 16 years past Franklin, but he was born 30 years after Franklin was born. So basically they lived at the same time. Now, I named some of the things that Benjamin Franklin did. One thing I left off is, back when we were a colony of Great Britain, he was an ambassador to France. I said he was quite a statesman. Well, guess who was a good physicist in France? Charles Coulomb. Now, you can't tell me, or you could, I couldn't help but believe you, but my guess is Benjamin Franklin and Charles Coulomb got together and compared notes because they were both studying electricity. Well, here's what Coulomb's known for. The charge on a proton is denoted by the symbol, let me get my pen set up. The charge on a proton, I write a proton with P+, Okay? The charge, they say, is E plus. It's exactly the same as one electron charge, only it's positive. So the charge on a proton, which is a positive charge particle, is exactly the same as the charge on an electron, only it's positive. Okay? Now, in the study of electricity, a much larger unit of charge is required, and because an electron charge, oh yeah, I forgot to say it, the charge on an electron is E minus, okay? Now those charges, the E is incredibly small. I mean, an unbelievably small number. You can't measure it with any device I don't think we have. It's just too tiny. So what they do, they study large numbers of electrons, and they use a symbol for that. So the measurement of the unit charge, okay, I'm sorry. The much larger unit of charge is required, and it's called, named after Charles Coulomb, a coulomb. C-O-U-L-O-M-B. Because it's named after someone, it's given the symbol capital C. Now, unfortunately, there's several things that use capital C. Degrees Celsius also uses capital C, but it always is followed or preceded by a degree symbol. Coulomb is not. So if you see 75 capital C, that is 75 coulombs. Okay? Named after Charles Coulomb. The measurement of the unit charges gives a positive charge, E, is equal to 1.60, positive by the way, times 10 to the minus 19 coulombs. That's how terribly tiny one electron charge is. 10 to the minus 19. So if you were writing that out as a decimal number, you would put 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. That many zeros before you ever get to the 160, okay? That is an incredibly small number, okay? Now, the other way of looking at that, if you had a charge of 1 coulomb, that would take you collecting 6.25 times 10 to the 18 electrons. Okay? Okay? So that means you would have to have, I'll get this one, 6, 250, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. You'd have to have 8 or 16 zeros following that 6,25. That is an enormously large number of electrons to make 1 coulomb. Okay, 1 coulomb of charge. So what that relationship is 1 over 1.60 times 10 to the minus 19 is exactly the same as 6.25 times 10 to the 18, and that would be 1 coulomb. This number of electrons, okay, that would be 1 coulomb. Okay. In fact, they say 1.00 coulomb because you have 3 significant digits in both of them. Okay. Now it says, although it seems like a lot of electrons, it represents only the amount of charge that passes through a 100-watt bulb in about 1 second. Okay? It's just they're so incredibly tiny, it takes so many of them to make any measurable charge. Okay? Now, one of the things that Coulomb discovered when he was studying these charges and things, he discovered that existence of what they call the inverse square law for charged particles. And that law was basically given his name. Okay? This works for electricity. It works for gravity. It works for light. It works for magnetism. Just about all these things follow an inverse square law. Now, gravity is a much weaker charge than electrostatic, but it is significant. Okay? So here's Coulomb's law of electrostatics. I think I'll write it here. The force between 2 point charges okay, we'll call it Q1 and Q2. And by the way, in this chapter, and probably pretty much what we'll be doing, little q represents charge. Okay? It's the parameter that means charge. Measured in coulombs. Okay? But it's charge. So here's 2 point charges, Q1 and Q2. The force between those is directly proportional to the product of their charges. That means you multiply them together. Okay, that's Q1 times Q2. Okay, and inversely proportional to the square of the distance between them. Square of the distance between them. Okay, that's Coulomb's law. Written in equation form, force, this is why we studied forces back in chapter, what was it, 5, somewhere back there, because you have to know forces to understand electricity, is equal to, now it said here, I'm going to actually rewrite this, is proportional to, that's what it said, directly proportional to the product of the charges, Q1 times Q2, inversely proportional to the square between them, the square of the distance between them. That's your proportionality equation. To make it an actual equation, not a proportionality, you change the proportionality sign to equal K. Okay? Equal K, where K is called the proportionality constant. Now, the actual name for that is sometimes called Coulomb's constant. Okay? Now, in SI units, which is what we use in all electricity, SI units, and by the way, if you remember, the French were the ones that really did a lot of the early work with Benjamin Franklin's help. The French were the ones who came up with the SI units. Okay? And since electricity developed after they had the SI units, everybody agreed not to come up with a set of new units for the U.S. customary or British system, but just to use the SI units. So that's why when you get electricity, and generally magnetism too, you don't have two sets of units anymore. With forces and weights and mass and all those things, you have two different systems. But when you get to electricity and magnetism, you have one system, that's the SI system. So in the SI system, this K is, it's a constant, and it's 9.00 times 10 to the 9th, and get these units. Newton meter squared per Coulomb squared. Okay? Now there's a reason for that, and we'll see that in just a minute. Okay, force is in newtons. Okay? Coulomb's constant is in Newton meter squared per Coulomb squared. That's a capital C Coulomb. Your charges, Q1 and Q2, are in coulombs times coulombs. So your Coulomb squared go out, and your R's are in meters. So that would be R squared and meter squared. So meter squareds go out, and you get newtons equal newtons. That's exactly what you want them to be. Those are the units that represent Coulomb's law. The force in newtons is equal to Coulomb's constant, which is 9.00 times 10 to the 9th Newton meter squared per Coulomb square, multiplied by the product of the two charges, that would be in Coulomb squared, so you wipe out the per Coulomb squared, and then divide it by the distance between them squared, which would be in meters squared, and that wipes out those, and you have newtons equal newtons. Okay. And I said the distance between is measured in newtons. In meters. Okay. All right. Let's do example 1. Can I erase what we got here? Yes. Okay. Anyone need it a little bit longer? Oh, you don't? Okay. All right. Two charges, each with magnitude 6.50 microcoulombs. So here's Q1, and it's equal to Q2, and equal to, these are charges, 6.50 microcoulombs. Now, does anyone remember what the metric prefix micro represents? Starts with the M, and if it were a big number, you'd like to be one. Million, okay. But this is a small number, so it's 1/1,000,000th. So this would be, the other way to write this is 6.50, and micro means times 10 to the negative 6 coulombs. Because 10 to the 6 would be 1,000,000, 10 to the negative 6 would be 1/1,000,000th. Okay, really small number. Okay, microcoulombs are 10 to the negative 6 coulombs, separated by a distance of 0. And those are the charges. The distance here, and we were calling that R. I like to call it D, but this book calls it R. R is equal to 0.200 centimeters. 0.200 centimeters. Now, just to get an idea about what 2/10 of a centimeter is, I don't have a dime on me, but I do have 2 pennies. I can't even count my money. Okay? These pennies are about 1 millimeter thick. A millimeter is 1/10 of a centimeter. So here's the distance, 2 pennies thick. Maybe a little too wide, but pretty close. 2/10 of a centimeter. That's it. That's the thickness. That's the distance between these two charges. Okay? Well, we don't want to be in centimeters either, do we? What does centi stand for? Yeah. Centimeters. What does that stand for? How many meters is a centimeter? Remember those pennies I just had? What are they called? What's the value? 1 what? Which is 1 cent. Right? Isn't that a penny? 1 cent? 1 penny? That's 1 centy dollar, 1/100th of a dollar. You're absolutely right. So this would be times 10 to the 100 is 2 minus 2 meters. So centimeters is 10 to the minus 2 meters. Okay, we usually don't write a decimal with it like that. So let's move the decimal place 1 unit to the right, making it 2.00. I just made the number larger by a factor of 10, so I need to make the exponent smaller. That's times 10 to the minus 3 meters. And like I said, 1/10 of a centimeter is a millimeter, and a millimeter is 10 to the minus 3 meters. Milli, 1,000. Okay, so that's your distance between. Pretty small. Okay. It says find the force of repulsion between them. What does Coulomb's law say? F is equal to, anyone remember? Coulomb's law. Just had it written down. K Q1 Q2 divided by R squared. Okay? Remember what K was? 9.00 times 10 to the 9th. You can check that and see. Units of Newton meter squared per Coulomb squared. Don't forget your units. They're your friends. Okay? And let's multiply that by Q1, which is 6.50 times 10 to the minus 6 coulombs, times Q2, which is also 6.50 times 10 to the minus 6 coulombs. Okay? And divide all that by R, which is 2.00 times 10 to the minus 3 meters, but we're going to square that. Okay? So this will be 4.00 times 10 to, and when you square an exponent, I don't know why that did that, you double the exponent, so 10 to the minus 6 meter squared. You also square the unit as well. And is it going to come back today or not? No. What a pain in the neck. Okay. I didn't realize. I'm going to lower the screen just a little bit more. Not that it really matters. But it seems like it's just a little higher than I thought. Not much, but a little bit. Okay. Now I've got to somehow manage to find some way to get this really gets to be a pain in the neck or some other body part. Is it doing anything now? There it is. So now I've got to get back upright. Okay. There we go. All right. So, what we've got to do, pull out your calculators. 9, you don't have to put the 0.00 if you don't want to. Remember how you do scientific notation? EE or EXP, 9. Oh, let's do the units first. Look at that. Okay. Here's a Coulomb square. There's a Coulomb and a Coulomb. They go away. Here's a meter squared down here. It wipes out that one. So you're left with newtons, which is the right unit. Okay? Now, so let's do the numbers. Okay? 9 EE or EXP 9 times 6.5. You don't have to put the 0 if you don't want to. EE or EXP negative 6 times 6.5 EE or EXP negative 6, then divide it by 4 EXP or EE negative 6. Okay? So, if you don't mind, I'm just going to take care of some of the 10 to the minus 6s. Let's wipe this one out with one of those. Okay? And that'll make life a lot easier. Okay? So, by doing that, now let's go back. 9 EE or EXP 9 times 6.5 EE or EXP minus 6 times 6.5. You don't have to put an EE there because we wiped out the 10 to the minus 6. divided by 4 equal. See what you get. Anybody? Just looking at it, it looks like it's going to be a number that's 10 to the third approximately, maybe 10 to the fourth. Okay. And I would say yeah. Okay. What do you get? 10 to the fourth. Yuck. I don't know why this goes away.
Can I ask you a question?
Sure.
Okay, you get rid of 10 to the negative 6, you get rid of both of those, right?
No, just one in the numerator, one in the denominator. Yeah. Okay.
You get rid of both of those. One of them.
One in the numerator, one in the denominator, right. Okay.
So then you just multiply the 9.00 times the 10.
Okay, but but you sure you use that EE or EXP 9. Don't do times 10. You'll probably get something wrong then. You might not. If you do it right, you'll get it okay. But it's so much easier. 9 EE or EXP 9 times 6.5 EE or EXP negative 6 times 6.5, you already got away with rid of the other one, divided by 4 equal. What do you get?
Well, I'm looking at the book. I know what you're saying, but I'm looking at the book, and it says the denominator is 2.00 times
10 to the minus 3
right.
squared.
Oh, okay, squared.
And then I squared it. 2 squared is 4, and when you square the negative 3, it becomes negative 6. You double the exponent. Yeah. Okay. Anyone do it yet?
9.51.
That sounds right. 9.51 times 10 to the, I was saying it looked out about to the fourth, and that's what it is, newtons. Whoa, that's a pretty big force, isn't it? 95,100 newtons. That's a pretty big force for such little charges, okay? And this is such a pain in the neck. I don't know why it does this. It was doing quite nicely tonight until now. Okay. Now, that was your first and only example so far in Chapter 17. And now we finish 17.3, and you have any of the odd problems 1 through 7. Okay? Basically, they're all going to use some form of Coulomb's law. F equal Q, or K, times Q1, Q2, divided by R squared. All right. Now, we're going to enter a new field here. Yes. Is it time?
I believe it's 6:28. I got to be at work at 7.
Oh, my goodness. Okay. Wait. What time is it now? 6:28?
Yes.
And we're supposed to be through at 6:30. Okay. So I guess we'll start next time with, boy, time flew tonight, didn't it? Of course, I went over that one announcement about 15 times. So, no, 4 times. So we'll start next time with 17.4. So you got a few homework exercises you can play with. And let me erase this one. All right. So just to give you an idea where we are and where we're heading, we're in, got it. Thank you.
16.
Wow, that's fast.
Do you possibly have a copy of 17?
I do. Well, I mean, I have the original. Whether I have a copy or not, let me see. And okay. Looky there. Okay, now there's not much you can do with it yet.
No.
You can do, I think, 1 and 2.
Oh. Yeah. I don't know.
Maybe 3. But that's about all you can do so far. And we'll be covering the rest of these. So if you can listen to your YouTube videos.
I'm just going to say, if not, I'll wing it.
Yeah.
All right.
Yeah, but yeah, you can wait until you get back and then pick it up then. So that at least gets you started.
All right.
Okay. All right, good deal. Just to give you an idea, we got through 17.3. We got 17.4, which is a little bit longer section. 17.5, which is a fairly long section. 17.6, which is a pretty, well, not that long a section. And then 17.7 is pretty long, okay? And 17.8 is about the same. And let's see, 17.9 is about the same again. So I doubt if we're going to finish all these. But if we don't get them all finished, then we'll stop and I'll tell you how far you need to go. This is sort of a long chapter. Oh, sorry about this. I probably did more than I should have to begin with. We were supposed to start it with 17.3, then 17.4, 17.5. We need to do 17.6. We'll stop at 17.9. We won't go any beyond that. So I think we may be able to finish. Maybe. We'll see. Good deal.
Thank you.
All right. We'll see you on Thursday.
All right. Gotta go to work. You'll see me.
All right.